next exercise 40. So here we have to determine the check digit for a money order whose identification number is this. So to find the check digit, you have to find the remainder when you divide this number by 9, and you can directly calculate and see that you have this. The check digit is 7234 541 780 not 9, and this turns out to be equal to 5. You perform the division actually and you find the remainder, you will see that the remainder is 5. An exercise 41. Suppose that in one of the non-check positions of a money order number the digit 0 is substituted for the digit 9 or vice versa. Okay. Prove that this error will not be detected by the check digit. Prove that all other errors involving a single position are detected. So we have a money order number which you know has two parts. One part is the number itself, and that is accompanied with a check digit. So if in the non-check position, that is in the number itself, we write the digit 9 for 0, or if there is a 9, we write 0 in place of 9. If we do that, then we have to prove that this error, then definitely because we have changed the number, we have committed a mistake, there is an error. This error will not be detected by the check digit. That is, the previous number and the new number will have the same check digit. And we also have to prove that any other errors involving a single position will be detected by the check digit. So we have to now prove this. So we start by considering a money order number. Let a money order number without its check digit be this number A9, A8, etc. up to A1, A0 in decimal system. It has 10 digits. These are the digits from A0 through A9. These are the digits of the money order number. Note that this number actually means this: A9 times 10 to the power 9 plus A8 times 10 to the power 8. It will go like that. A1 times 10 plus A0. Now since ten mod 9 is equal to 1 mod 9, whether you divide 10 by 9 or 1 by 9, you get the same remainder, which is 1. So that's why they are equal. We get mod 9. So this is the check digit. This remainder that we have here will be the check digit for the money order number, which is equal to, if you use this expression, this becomes A9. Use the rules of modular arithmetic. Since 10 mod 9 is equal to 1 mod 9, so 10 to the power 9 mod 9 will also be equal to 1 mod 9. If you multiply that on both sides by A9, you will then have A9 10 to the power 9 is equal to A9 mod 9. Okay, so this is equal to A8 plus etc. plus A1 plus A0 modulo 9, and in fact this again becomes A9 mod 9 plus A8 mod 9. In carrying out this calculation, we are using the many previous exercises where we encountered some properties of this modular arithmetic. Mod 9 mod 9. Okay, Now since nine mod 9 is equal to 0 mod 9, clearly both the sides are 0, so that's why if in place of these remainders, these mods, you have say 9 here, then whether you write 9 here or 0 here, it does not matter. And conversely also, if you have a 0 digit, then in place of that you can write 9. You can, and actually that will be a mistake, but because of this equation, that mistake will not be will not reflect on the check digit. The check digit will continue to be the same since this. So the language is this, the check digit stays unchanged. Stays unchanged if in a non-check position if in a non-check position the digit 9 or the digit 0, same thing, the digit 0 is substituted for the digit 9 or vice versa. Also, since I mod 9 is not equal to j mod 9 for all distinct I and j belonging to this set, every error involving a single position and a substitution other than the above, that is the one involving 0 and 9. If we substitute any other digit with something else, then that will be detected, then the check digit will not be the same. So its change will tell you that you have made some mistake. Will be detected. Okay, so next (42). Suppose that a money order identification number and check digit of 2172 042 1168 is erroneously copied as 27750421168. Will the check digit detect the error? Okay, let me feed it some ink. So here a money order identification number is given along with its check digit. You can see that the first part of this number, I mean except the last digit, that is the money order identification number. How many digits are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, just like what we considered there. And the last one is the check digit. This is the remainder when you divide the rest of the number by 9. Now someone has made a mistake in copying the number and they have written this. The check digit continues to be the same, but now we are being asked whether the check digit will detect the error. In other words, for this new number, obtained by removing this 8, we get a new number, whether that also leaves the remainder 8 when divided by 9. If it leaves the same remainder, then despite having an error, the check digit will fail to detect the error. And in fact, that's what happens. In this case, the check digit is unable to detect an error. Will the check digit detect an error? Solution: no. Will not detect an error because 2172 04 to 116 mod 9 is equal to 8, which is also equal to 27750. 4 to 116 mod 9. You can verify this directly. So the check digit fails to detect the error. Then exercise 43, a transposition error. Involving distinct adjacent digits is one of the form Okay, so in place of AB, someone accidentally writes BA. That type of error, weak. A not equal to B, of course, because if A is equal to B, then this is not an error. In fact, nothing changes. Prove that the money order check digit scheme will not detect such error unless the check digit itself is transposed. Okay, so if one commits a transposition mistake like this, then it will be detected, it will not be detected if the transposition mistake is in the non-check position, but a detection is possible only when the check digit itself is transposed. For example, in place of writing this, someone writes all the numbers correctly except while writing 68 he writes 86, then the check digit has been transposed with its adjacent digit. Okay, so the solution here actually depends on one of the previous exercises, but before doing anything we have to consider the money order number. Let a money order number I am writing without its check digit, but I think you can simply write a money order number. The check digit, although it's written with the number, it's not a part of the number, but it is something that comes with the number. But just for the sake of clarity, we are writing without its check digit B, A9, A8, just like before, A0 in written in decimal system. So when we write written in decimal system, then it means that these are decimal digits from 0 through 9. Had they been in binary system, each AI would be either 0 or 1. Okay. Now we have already seen in the solution to exercise 41 that the check digit for this money order number is this. This is something we have already seen in that solution. Mod 9. Okay. So you can see that if you are transposing to adjacent digits in any of the non-check positions, for example A1 and A0, you transpose A1 and A0, then this sum does not change. In place of A1 you will have A0, in place of A0 you will have A1. That does not change the sum at all. So the check digit also it remains unchanged, so that does not affect the check digit, and as such a mistake or such an error will not be detected by this check digit. So we can write like this. So a transposition error will not be detected by the check digit if check digit itself is not involved in the transposition. But what happens if we transpose the check digit itself with, of course, its adjacent digit, because that is the kind of thing we are considering, involving two distinct adjacent digits. Next, let the check digit, we have to assume distinctness also. Yes, we can start like that. Next, assume C2 not be equal to A0, and we will transpose A0 and C. Let C be transposed with A0. Okay, now this error will be undetected or rather I should have written will not be detected. Okay, this sounds wrong. If and only if A9 plus A8 etc. plus A1 plus A0 mod 9 is equal to A1 plus C mod 9. Instead of writing if and only if, we can write this double implication that also has the same meaning, if and only if. So you can see that these things can be cancelled out, leaving us with this A0 mod 9 is equal to C mod 9. Now note one thing, that C is the remainder when you divide this sum by 9. That means C has to be strictly less than 9, and C is a non-negative integer. So C mod 9 is actually nothing but C itself. Okay. This means that if, now note that you cannot immediately conclude something that will contradict this one. A0 mod 9 and C mod 9 being equal, or the equality of A0 mod 9 and C does not immediately say that C has to be equal to A0. C is less than 9, but there is nothing that is telling us that A0 also has to be less than 9, because after all A0 is a decimal digit. So A0 may very well be equal to 9. If A0 is equal to 9, then C will be equal to 0. And 9 and 0 clearly are not equal. Modulo 9 they are considered to be equal, but that is something else entirely. In this case C is 0 and A0 is 9. So you can see that in such a case also the error will not be detected. But of course, if this equation fails to be true, then the error will be detected. So the error detection is possible only when the check digit is transposed. if something else is transposed, then it will never be detected. That's what the exercise is saying. This means that if C is not equal to A naught mod 9, or because we have worked for if and only if, we can continue to write that, except in a different manner. So this means that this is not equal to A naught if and only if the error in the transposition the language is not good here. Not the error in the transposition, the error resulting from the transposition is detected by the check digit. Okay. And it makes sense also. You see, if you perform this transposition, then looking at the resulting number, you will think that A naught is the check digit. Now, if the remainder of the rest of the number obtained after removing A naught from this new number, modulo 9, that is when you divide by 9, if that remainder fails to be A naught, then you know that something is wrong, and that remainder is nothing but C mod 9, which is C. So if C fails to be equal to A naught, then you know there is something wrong. One more thing is that if A naught is equal to 9, then you can immediately say that the number is not correct, because the check digit is a remainder when you divide something by 9. So it cannot be equal to 9, it will always be less than 9. So if you have 9 in place of A naught, then this type of transposition will, you don't have to do anything, you don't have to in fact perform the division to find the remainder, or in other words the check digit. You can directly say, because A naught is equal to 9 and check digit is less than 9, so there is a problem, the number is not correct. Okay, then exercise 44, determine the check digit for the Avis rental car. With identification number 540047, and for this it has been asked that It has been suggested that we look at example 5. Now here the calculation is modulo 7 because that is the system AVs uses. And you just have to find the remainder when you divide this by 7. So the solution is this. Pretty straightforward. Mod 7, and it turns out to be equal to 4. So that's just it. Then exercise 45. Show that a substitution of a digit ai prime ai prime for the digit ai, where ai prime and ai are not equal in a non-check position of a UPS number, United Parcel Service number, is detected if and only if this condition is true. This is not equal to 7. Okay, now we are going to consider a UPS number. A8, A7, etc. up to A1 and A0 in decimal system. Okay. For a digit ai prime not equal to ai, substitution of ai prime for ai is not detected if and only if and only if the check digits remain the same. I mean the check digit remains the same. us write here. It starts from A8. Mod 7 is equal to, if in place of AI we substitute AI prime, everything else remains the same. If and only if, cancelling equal terms, you get ultimately this. Or let us write this one first. AI times 10 to the power I mod 7 is equal to AI prime times 10 to the power I mod 7. If and only if AI minus AI prime mod 7 is equal to 0. We have already seen that this means that this number, this integer, this difference times 10 to the power I is divisible by 7. Now note that 7 and 10 are relatively prime. As such, 7 and any power of 10, any non-negative integral power of 10 is, they are also relatively prime. So the fact that 7 divides this product implies that 7 has to divide this. So that means this is equivalent to AI prime mod 7 being equal to 0. In fact, in brackets you can write, since GCD of 10 to the power I and 7 is equal to 1. Okay. Now notice this inequality. AI prime and AI are not equal. They are decimal digits, but they are not equal, and yet their difference is divisible by 7. So that means since they are decimal digits, at most they can be what? 7. They can be 7, but at the same time they are not equal. So if one of them is 7, then what about the other? I mean, what I am trying to say here is that what are the possible values of this difference? Since this difference is to be a multiple of 7, the possible values are this: plus minus 14, plus minus 21, etc. But since these are decimal digits, we will never have these values. Plus minus 14, plus minus 21, they can never be obtained, no matter how hard you try. So the values are restricted to be either minus 7 or 0 or plus 7. Okay, can it be 0? For this to be 0, since AI and AI prime are both decimal digits, this will be 0 if and only if they are equal, but they are given to be not equal. So there is no possibility of having 0. So the only possibility is that this difference is either plus 7 or minus 7, and as such the absolute value of this difference has to be equal to 7. So we write like that. Since AI is not equal to AI prime, we have AI minus AI prime mod 7 equal to 0 if and only if this absolute value is equal to 7. What have we proved here? The substitution error is not detected if and only if this is equal to 7. We can say it in another way, namely that the substitution error is detected if and only if this is not equal to 7, and that's what we have to prove. So the given substitution error is detected if and only if this is not equal to 7. Okay, and keep in mind this is for that rental car. There this system is used where the modulus is 7, unlike the United Parcel Service where the modulus is 9. Or the money order identification number, there the modulus is 9. In United Parcel Service also the modulus is 7. Okay. Now next exercise 46. Determine which transposition errors involving adjacent digits are detected by the UPS system, UPS check digit. Okay. So the starting is like before. Let a UPS number be this A1 A0 in decimal system. Okay, so now we have to look at two different cases, namely the transpositions where the check digit is not involved and one where the check digit is involved. For an integer, the transposition error AI plus 1 is changed to AI plus 1 AI is undetected. Yeah, we are working with undetected because then only we get an equation and we can work with that equation. Is undetected. So previously what we were doing, previously we did not have transposition error, previously we had substitution error. Okay, that is something different. In place of a single digit we brought in something else, but for transposition we are transposing or interchanging the places of two adjacent digits. Okay, so this is undetected if and only if A8 10 to the power 7 A7. Oh, this time we are writing the powers of 10 first. Same thing, A1 plus, oh, I have to write the things that I am transposing. I plus 1 AI plus 1 plus 10 to the power I AI plus etc. 10 A1 plus A0 mod 7 is equal to to the power I plus 1 but AI. Plus 10 to the power I AI plus 1 and the rest of the terms are same. Plus A0 mod 7. This equation is equivalent to 10 to the power I plus 1. Here we have AI plus 1, here we have AI. AI plus 1 minus AI. Okay. And then here we also have 10 to the power I AI and there 10 to the power I AI plus 1. So minus 10 to the power I AI plus 1 minus AI mod 7 equal to 0. Now what we can do is we can take 10 to the power I times ai plus 1 minus ai common out. Doing that will give us times 10 minus 1, that will be 9. This is equal to 0. Again gives the fact that both 9 and any power of 10 are relatively prime to 7. So that gives us minus ai mod 7 is equal to 0, since this is 1 and this is also equal to 1. Okay. That transposition error, or we can write like this, since the transposition error is to be an error we must have ai not equal to ai plus 1. Because if they are equal, then transposing them will not change anything, so we won't get any error. So for this to be a legitimate error, ai should not be equal to ai plus 1. But then by how we argued in one of the previous exercises, this implies and is implied by this is equal to 0 if and only if this is equal to 7. Now this is a transposition involving digits that are in non-check position. Now what happens if we do this with the check digit? Next, if the check digit C equal to, don't make the mistake of writing C equal to A8 plus A7 plus etc. That was in the case where the modulus was 9, because 10 was 10 mod 9 is equal to 1 mod 9. Here the modulus is 7, so we don't know whether the check digit is the sum of the digits. It may not be, and in fact it will not be in most of the cases. So here you have to write the full expression. A7 plus etc. 10A1 plus A0 mod 7. If the check digit is transposed with its adjacent digit, which is A0, then this error or error under the assumption that C is not equal to A0. Just like we needed the assumption that AI plus 1 is not equal to AI, because then only it's a error. So here also that assumption must be there. Then this error is not detected if and only if A1 plus A0 mod 7 is equal to this. Plus C mod 7. If and only if A0 mod 7 is equal to C mod 7, which is equal to C, because C is the check digit and modulo 7 means it will be less than 7. It's the remainder that this number leaves when we divide it by 7. So by definition it's less than 7, so C mod 7 is equal to C. Equivalently, the transposition error resulting from transposing C and A0 is detected if and only if C is not equal to A0 mod 7. So we have now seen all the possibilities of when an error will be detected and when it will not be detected for a UPS number. Okay, then exercise 47. If you want, you can simplify this expression, I mean this condition, by claiming that this is true if and only if this is true. You can try it. It's somewhat like that other condition we had done in that other exercise, or if you want you can just keep it like this. Okay, next we come to the UPC system. Use the UPC scheme to determine the check digit for the number so in UPC scheme we form a vector using the digits of the given number and take its dot product with a fixed vector and then calculate that dot product modulo 10, that should be equal to 0, and the last digit is the check digit. So for the number for this number 073 124 00508. So this is the number and the last one 8, that digit is the check digit. Oh no. I think what I said is wrong. No, that is not the check digit. The check digit will now be found. That's not the check digit. Let me just see. 1, 2, 3, 4, 8, 9, 10, 11. Okay. Oh, so for, in a UPC scheme, the number along with the check digit, it forms a 12-digit number. So the given number here has 11 digits. So we have to find the check digit. Yes. So let A be the check digit. Then you calculate the dot product of these two vectors 7 3 1 2 4 0 0 5 0 8 dot 3 1 3 1 3 1 3 1 the last one should be 8. 1 2 3 4 5 6 7 8 9 10 11 12 2 3 4 5 6 7 8 9 10 11. Yeah, because then only it ends with 1. This dot this mod 10 should be equal to 0. So you can calculate 7 times 1 plus 3 times 3 plus 1 times 1 plus 2 times 3 plus 4 times 1, this 2 will be 0, plus 5 times 3 plus 8 times 3 and finally A mod 10 is equal to 0, and this gives us ultimately 66 plus A mod 10 equal to 0, and that implies A is equal to 4, because if A is 4 you get 70 mod 10 is 0. So this is the check digit 4. So in the UPC scheme, this number will be appended with 4, that extra check digit. Next exercise 48. Explain why the check digit for a money order for the number capital N. N is some positive integer. Is the repeated decimal digit in the real number. So if capital N is our money order number, then we already know how to find the check digit. Just divide N by 9, the remainder will be the check digit. But curiously, the check digit also turns out to be the number or the digit in the decimal expansion of the number N by 9. If you perform this division and write the result in decimal form, after the decimal point, a digit will be repeated always. That digit turns out to be the check digit. We have to explain why. By the division algorithm, there exist unique integers Q and R such that, so that means if we divide N by 9, we will have a quotient and a remainder. That's what I am writing here, such that N is equal to 9Q plus R and the remainder R is non-negative and less than 9. So by definition of check digit for a money order number, this R is actually the check digit because it's the remainder when you divide N by 9. So the check digit is R. Now one can verify that the decimal expansion of R divided by 9 is 0.RRR etc. it's not very difficult. There are only finitely many choices. No, you just verify them one by one. This of course is obvious. This if you calculate, it will turn out to be this. If you calculate 2 divided by 9, it will be etc. all the way up to 8 divided by 9. Note that r can be at most 8. So because of this, the decimal expansion looks like this, and it makes sense also because r is a digit that is less than 9. So what do you get when you divide this on both sides of this equation by 9? You get this. N by 9 is equal to q plus r by 9. Now since q is a positive integer, note that capital N is positive, so q is positive, r is also positive, and capital N is a check digit number, so this capital N is not less than 9. When capital N is less than 9, q will be equal to 0 and r will be equal to n. That case does not arise. I'm losing my words. Money order number is always greater than 9. In fact, it has many digits. No? So since this, the decimal expansion of n divided by 9 is simply this q point r etc. So you can see that in this decimal expansion of n by 9, the check digit is the repeated decimal digit in the real number. So that's what we had to show. Then exercise 49. The 10-digit ISBN, International Standard Book Number, you will find this number in books which are published under some good publishing company. ISBN 10 A1. Okay, they had to write it entirely. Has the property has this property. its dot product is also 0 with some vector. I mean, its dot product means the vector that you would get from this 10-digit number. If you take the digits and form them, you form the vector's components. With a fixed vector is 0 but modulo 11, and this is the property. A1, A2, like this up to A10 dot 10, 9. Now we are no longer taking 3, 1, 3, 1. 8, 7, 6, 5, 4, 3, 2, 1. Mod 11 is equal to 0. The digit A10 is the check digit. When A10 is required to be 10, to make the dot product 0, the character X is used. If the check digit turns out to be 10 itself, then I mean, if it is equal to 10, if it turns out to be equal to 10, then we use X in its place. Is used as the check digit. Verify the check digit. For the ISBN 10, assigned to this book. This book means this book from where we are taking all the exercises, contemporary abstract algebra. So the ISBN, if you search in the book, in the beginning itself it's given the ISBN number for this book is given to be this number 113359970. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 10th one is the check digit, that is 2. We have to verify this, that this is true. We see that to verify this you just have to see whether this condition is true. 1 times 10 plus 1 times 9 plus 3 times 8 plus 3 times 7. So this is the dot product we are calculating, plus 5 times 6 plus 9 times 5 plus 9 times 4 plus 7 times 3 plus 0 times 2, we need not write, plus 2 times 1 mod 11. This sum turns out to be 198 mod 11, and 198 you can clearly see is divisible by 11 because 1 plus 8 is equal to, in fact it is 18 times 11. 1 plus 8 is equal to 9. So that's why the ISBN assigned to this number is correct. I mean this is assigned and this is the check digit. This number likely has information about the publisher, what type of book the book is, etc. And then exercise 50. Suppose that an ISBN 10 has a smudged entry. That is, one of its digit has a smudge. It cannot be seen anymore. One cannot make it out. Smudged entry. Oh, so UG, smudged entry where the question mark appears in the number. So this is the number 0716, and then this one cannot be made up. 28419. 2841, and there is a hyphen 9. Determine the missing digit. Let A be the missing digit. Then that same condition, 0 times 10 plus 7 times 9 plus 1 times 8 plus 6 times 7 plus, am I writing it correctly, plus 5 times A, 4 times 2. Actually I should have written 987. Oh, see, okay, yes, I made a mistake. 987, so this will be 6A. 5 times 2 plus 4 times 8, 3 times 4, 2 times 1 plus 1 times 9. Mod 11 should be equal to 0. and this turns out to be equal to 178 plus 6a mod 11 is equal to 0. Now 178 mod 11 becomes 2. 2 plus 6a is equal to 0. So this implies a is equal to 7, because then you get 44 here, and that is divisible by 11, and 7 is also less than 11, so 7 is the unique solution. You can write, so the missing digit is 7. So that will be all for today. Here I end this exercises. There are more, but that we will see in the next video. So that's all. The signing off for today. This is me, Lucifer, from the mathematical room. Have a nice night.